Brilliant. So first of all, thank you for inviting me to talk. It's a pleasure to talk to such an enthusiastic group within the OU. So over the next 30 to 40 minutes, I kind of want to give you a flavour of the way we study asteroids across the field. I'll dive a bit more specifically into how I observe asteroids with the Open University's very own OpenScience Observatories. I want to give an overview of the research that I've been conducting and putting out lately. And at the end, I want to give everyone some information how you can get involved with the observatories, no matter where you are or who you are. If you want to get in contact with me after the talk, feel free to just head over to my website, and my contact information is on there as well. Or just ask me for my contact information in the chat after I've finished talking. So the first thing I want to say is that I have some interactive components to my slides. So if you head over to slido.com and enter the code OUSS, you can answer polls and questions that I'll put up at various points throughout my slides. So it's not crucial that you do, but it'd be nice to get some back and forth interaction between everyone. And if you've got a smartphone, just scan the QR code. I know we're all very familiar with scanning QR codes nowadays. So if you want to do that, just head over to there, and I'll put this information up before the first interactive slide, just in case anyone misses it now. Okay, so I'll just give myself a quick introduction again. So as Joe said, I'm Samuel L. Jackson. Unfortunately, I'm not that one, as you may have guessed. I'm currently a third-year PhD student at the OU within the School of Physical Sciences, working with the OpenScience Observatories. I originally hail from sunny Southend-on-Sea. I moved to Canterbury to do my integrated masters at the University of Kent, where my master's project actually also involved doing telescope observations of asteroids. And now I'm based in Milton Keynes, where I work on the main OU campus, when we're allowed on the campus, that is. So approximately half of my research focuses on observational and theoretical studies of asteroids. The other half is kind of technical support, implementation, characterization and testing of telescope systems. And these halves are combined together into one cohesive project through the use of the OpenScience Observatories. And I'll come on to the details of the observatories a little bit later in the talk. So first, I'm going to begin with a very brief introduction to asteroids for those that may be unfamiliar. So asteroids are rocky bodies that are remnants of the formation of the solar system, or failed planets. They have very primitive origins, which mean their compositions indicate what the conditions were like in the early solar system. However, most of these have evolved significantly due to impacts and space weathering over billions of years. So we need to understand how these objects have changed in order to interpret their characteristics in the context of the early solar system. And you can see the variation in shapes and sizes on the right-hand side. So we've got asteroid Bennu, is 250 meters across. It's the target of the recent OSIRIS-REx mission by NASA. So it's covered in these really large boulders. It has this sort of spinning top shape, which is actually more common than you might think within the asteroid population. You've got the bigger asteroids, Eros and Gaspra, over 10 kilometers across each, peppered with impact craters from billions of years of impacts. And you can see some of those craters almost bigger than, or probably bigger than Bennu itself. And then we've got quite an interesting one, Itokawa, down there. It's got this heavy bouldering on it still, but it's got this potato-shaped but bilobate sort of structure. What this means is it has kind of two separate structures within the one asteroid. So they actually have two different densities on different sides of the asteroid, and this tells us about how it may have originated, and also makes for some interesting dynamics for how it will evolve in the future as well. So as of the other day, when I wrote this slide, NASA listed over 1.1 million asteroids that have been detected to date, although there will be many, many more discovered over the coming years and decades to come. And even though there are so many of these asteroids, the total mass of all of them combined is still less than that of our moon, which I think is really quite incredible considering just how many there are. So why do we want to know about these objects? Well, we need to understand how they've evolved to infer information about the early solar system, as I said before. But then there are very interesting processes like the Arkovsky Effect, where thermal heat radiated off the surface of the asteroid can actually act to change their orbits. And these sorts of effects are driven by surface properties and the shapes of the objects. Now, I'm going to give a quick explainer of the Arkovsky effect before I go back to that slide. And basically what happens is the sun heats up the asteroid, and that heat is later re-radiated, say a few hours later. And this imparts like a kick onto the asteroid. So it produces a thrust. And depending on what way the asteroid is rotating, this thrust is either in the direction of motion of the asteroid or against the direction of motion of the asteroid. And depending on which way round it is, it can either act to push out the orbit of the asteroid, so make it larger, or to cause it to drift inwards. And this is a really important effect among smaller asteroids. So if we come back here, if we look at the graph on the left-hand side, basically what we're trying to show here, I don't want to scare people off with too many graphs, but what we're showing here is the number of asteroids versus essentially the average distance that they are from the sun in what we call astronomical units. So one astronomical unit is the average distance between the Earth and the sun. And we can see that at certain distances from the sun, there are these large absences of asteroids in these positions. And this is because at these distances, their orbits are in what we call resonance with Jupiter. So, for example, here, if we take this 3-to-1 line, this means that at this around 2.5 astronomical units, an asteroid here will rotate 3 times, or will orbit 3 times for every 1 orbit that Jupiter makes. And this means that every time Jupiter completes its orbit, it sees the asteroid in the same position, or approximately the same position every time. And this regular gravitational tug that Jupiter is able to exert on the asteroid can actually affect the orbit of the asteroid and can fling it into these wild orbits and can send them careering into the inner solar system. And this is where we get what we call the near-Earth asteroids, ones that come close enough to Earth to potentially worry about. And things like the Arkovsky effect are really important here. So the near-Earth asteroids don't last very long. They last far less time than their counterparts in the main belt. And this is because they're more likely to impact with the inner planets or to be just flung into the sun, for example. So you think, oh, well, then eventually we'll run out of near-Earth asteroids because there's no more asteroids sitting in these resonance zones, and we'll eventually run out of near-Earth asteroids. But that's not the case, because things like the Arkovsky effect, which I showed you before, can push asteroids that are, say, here at 2.4 AU, can push it slowly over time into this resonance zone and then send it flinging into the inner solar system. So it's these effects which supply and sustain the population of near-Earth asteroids. So we need to understand these effects and therefore the properties that drive them in order to make threat predictions for the future. And we also need to know the properties of these individual objects so we can plan, potential mitigation strategies in the event that we find an object that is on a collision course with Earth. And that's kind of the purpose of the Double Asteroid Redirect Test mission that's recently been launched by NASA. Now, I won't go into detail on that because I can give a whole talk on that mission. But if you're interested, feel free to ask me after the talk. Now, aside from planetary defense, characterizing the surface properties of these asteroids will also be really important as we become more of a spacefaring civilization. So the potential resources that they have are enormous, and the opportunity to mine them should not be discounted. And I'm of the opinion that the first trillionaire will be someone who does something like this, who manages to bring back material from an asteroid, a particularly resource-rich one. So I said I'd put these instructions back up before the first interactive slide. So if you haven't had the chance to try to get onto Slido and use the code, do it now if you want to interact with the next slide. So the thing I want to know is, what do you see as the main reason why we should study asteroids? And hopefully it will work and people will be able to vote. That will give people enough time to get on there and vote. Thank goodness it's working. Whew. Okay, so we're seeing a lot of votes for understanding the early solar system. A lot of people arguing for planetary defense. It's good to see all the votes coming in. I like the 7% of you that have gone for just why not. It's a real astronomer's attitude. Okay, so I think I won't wait anymore, but so I see the majority of people have gone for understanding the early solar system. And from my personal perspective, I usually go down the planetary defense argument, but it's nice to see we have a lot of people coming from a pure science and curiosity standpoint here, which is really key as you go through your studies, to have this curiosity. Okay, so moving on. Now you may be asking the question, do we know where all of the asteroids are? And the unfortunate answer is no, we don't. Now the first caveat, this plot is a little old now, so it isn't an up-to-date reflection, but it's still mostly accurate. So what we're plotting here, in the bars are the number of asteroids found according to a given size, and the red line dictates how many asteroids we expect to find for that size based on theoretical models. Now you can see we know where all of the big near-Earth asteroids are. So if we think about the impact that wiped out the dinosaurs, the Chicxulub impactor, that was a few kilometers across, but we know where all of those are, and none of them are on a collision course with Earth. So yay, that's bully for us. However, we don't really know where a lot of the smaller asteroids a few hundred meters across or less are. If you remember back to 2013, pre-pandemic times, I know, where an impactor only around 20 meters across exploded above the city of Chelyabinsk in Russia. And despite this being so small, the air blast caused significant damage to windows and buildings, and luckily no one was killed, but many suffered injury from things like broken flying glass and things like that. And we haven't even begun to scratch the surface of detecting all of these objects because they're just too small. You can see, so this is a logarithmic scale. So, saying we've found maybe a few hundred of these near-Earth asteroids, but we expect tens of millions of them. So we've basically detected none of them, really. Now, to put this into context, let's look at the size that an impactor has to be to cause different levels of damage. So this was a table that I've stolen from a conference I attended last year called the IAA Planetary Defense Conference, where we discussed and simulated an asteroid impact exercise, working on it from discovery of the asteroid through information gathering to eventual impact and disaster mitigation strategies. Now, we see that a 50-meter impactor can cause local scale devastation. Something in the range of 100 to say 400 meters can cause anything from regional to continental scale devastation. And from 500 meters to a kilometer, we're dicing with a global scale event. And this doesn't even account for the human factor in all of this, the panic, loss of agricultural land, breakdown in law and order, in the run-up to impact, economic collapse. All those things aren't even taken into account here in the devastation types. So if we put this back into context on the graph from earlier, as I mentioned before, we see that we've probably got all of the global effect impactors and probably most of the continentals by this point. Like I said, this is a bit old, this plot. But the majority of those that would cause local to regional devastation, we quite simply don't know where they are. And we don't know if there is one with our name marked on it already. So on that happy note, I'm going to quickly pivot to a quiz slide. So if you can, join the quiz. You just have to enter your name so you can answer the quiz. I'll let some more people join. Oh, the real SLJ. I wonder who's trying to steal my name. Okay, so we're up to 34, 35. Let the last few trickle through. And as well, it's important to note, if you get the questions right, there's a nice slide at the end which calculates who answered all the questions right, and it'll throw some confetti on the screen. So, we're playing for real prestige here. Okay, I think the names have slowed down now. So let's go to the question. So you've got 20 seconds to answer. What is the largest asteroid in the solar system? Let's test what you know about asteroids already. A few seconds left for those stragglers. Okay, so 82% of you have gone for Ceres, and 12% for Itokawa, 3% for Gaspara, and 3% for the Moon. So as you may have guessed from the totals, the correct answer is Ceres. The Moon isn't classified as an asteroid. That was a red herring. Ceres is the largest and was the first discovered. It's also classified as a dwarf planet. And Gaspara and Itokawa are much smaller than Ceres. Okay, so let's move on from there. So it's important, now that I've mentioned planetary defense and impacts, to say that there are currently no known objects in the solar system that pose a realistic threat to Earth, as much as the tabloids might make you believe otherwise. And sorry, Tracy, this is why I dodged your question earlier. Hence the need for a wall of shame in this talk. So hear it from me. If you see a headline like this, don't run for the hills and start stocking toilet roll like everyone did at the start of the pandemic. You're going to be just fine, probably. And as much as I hate seeing these headlines, they really frustrate me. I do have to give it to this one with the leading line for Rocky Horror. Did really make me giggle a little bit. And here you can see Leonardo DiCaprio and Jennifer Lawrence in Don't Look Up doing an impression of how me and my supervisors react when we see these headlines. Just complete confusion. So if you have seen Don't Look Up on Netflix, you may have seen this scene where Jennifer Lawrence's character gets to overlay multiple images of the comet into one image and with a touchscreen identify the position of the coordinates of the comet in those images. Now, I tell you, if astronomical software was that user-friendly and quick, we'd have already uncovered all the secrets of the universe and I'd be done with my PhD by now. But as you can tell, I'm still a third year, so bad news. In reality, you'd be passing that data through various programs to extract sources, solve for the sky coordinates, write some scripts to identify where the comet is in each image, because you wouldn't want to do that manually, and do your orbital dynamics calculations and things like that. So it's definitely going to take longer than that. And grunt work like this is actually what takes up a lot of your time in research astronomy. And a fun fact actually about this scene is that these images are actually some of the discovery images of the comet Neowise that graced our skies towards the end of 2020, I believe. It was a fun little Easter egg that the scientific advisor on the film put in. Okay, so how do we observe these asteroids? There are three predominant wavelength ranges we observe them in. And the first I'll briefly touch on is radio waves / radar. So the main facility for this was the Arecibo radio telescope in Puerto Rico until it spectacularly disassembled itself at the end of 2020. Now, for those of you who haven't seen the collapse of Arecibo before, I'll play this video while I touch on what we get from radar observations of asteroids, and hopefully this will play okay over the over sharing the screen. So what we do is we send out pulses of radio waves and measure how they reflect off of the asteroid, both in terms of how long it takes them to get back, and how much their frequency changes. And we call this delayed Doppler imaging. And this allows us to measure the shapes, sizes, rotation rates, and positions of these asteroids very accurately. But you need a big dish with a very strong transmitter in order to achieve this. And Arecibo was by far the biggest and the best at doing this. Now, parts of NASA's Deep Space Network that's used to communicate with spacecraft throughout the solar system are used for this as well, but they have a lower resolution and are not able to reach as far as Arecibo could. And the ability of radar to measure the distance to an asteroid by measuring how long it takes the pulse to come back is the key factor in measuring the positions of newly discovered asteroids that may pose a threat to Earth. So our capabilities here are significantly impacted by the loss of Arecibo, and I really do hope the money is found to either rebuild it or to build some other facility of equivalent size. I know China have built a big radio telescope, but unfortunately it doesn't have a transmitter. I'm not sure how compatible it would be with the same techniques that Arecibo did. Okay, so moving on from radar, because that's not my specialism. Another wavelength range we can observe asteroids in is the infrared. So this is essentially where we're looking at the heat coming off of the asteroid. And this provides an ideal way to measure the sizes of asteroids. When we observe in the visible wavelength range, what we can see with our own eyes, we observe the light reflected off of a surface. So from a distance, a small but very reflective object has the same brightness as a large but not very reflective asteroid. But when we observe the emitted heat from an object, its reflectivity is irrelevant. So the brightness corresponds directly to the size of the asteroid. And these measurements of sizes of asteroids are the crucial first step for understanding their future evolution and their history. Now, I've touched on it already now in the upper part of this figure, so we're going to look more in depth at how we observe asteroids in the visible wavelength ranges, the stuff we see with our own eyes. And to do this, we use optical telescopes. So in my case, I've been making use of the OpenScience Observatories, two of which you can see here. The OpenScience Observatories is comprised of a 3-meter radio telescope on campus in Milton Keynes, which isn't capable of asteroid observations because it's too small and doesn't have a transmitter, and 2 automated optical telescopes in Tenerife, around 2.5 kilometers above sea level. Now, Tenerife has one of the best astronomical sites in the world. If you're ever in Tenerife, I can't recommend enough visiting the observatory. I don't think I'd ever known true darkness until I went out there to do some maintenance of the observatories. There was no moon or anything like that. I stepped outside of the residence, put my hand in front of my face, and I could not even see my own hand. It was surreal for me, someone who's grown up in places with lots of light pollution. So if you're ever out there, go. So the 2 telescopes we have is COAST, which is a 17-inch telescope, which is used for our free badged open course, processes requests from our telescope.org service, and is also used for research and satellite tracking work for our commercial partners. Pirate is larger and is our predominantly teaching and research telescope, and it sits at 24 inches. So it's 24 compared to 17, and that results in a doubling of the actual area of the mirror. So you collect twice as much light with the 24-inch. And some of you may have already had the opportunity to use Pirate through various OU modules. And it's these 2 telescopes I've made use of for my research over the past 2.5 years, but predominantly using Pirate. And this is because asteroids are generally quite faint, so you want to use the largest telescope you have available. However, when I first started, Pirate was actually the 17-inch telescope that now sits in COAST, and COAST had a much smaller 14-inch mirror. That was until last July, when a team from Barda Planetarium, the company that built the observatories to begin with, went out with a brand new 24-inch telescope that we bought for Pirate. And the 17-inch from Pirate was then moved into Coast, and the old 14-inch was donated to a local non-profit on the island. Now, the photos you see on the slides are from the upgrade process, and you can see the scale of the new 24-inch by comparing it to the people around it. The 17-inch you could actually lift with a team of people onto its mount, but for the 24-inch they had to get a small crane up the mountain to do it because it was just far too heavy. And apparently it looks even bigger in person than it looks in photos. I really hope I get to go out there again before the end of my PhD to see it. Now, it wouldn't be a telescopes related presentation without showing some pretty images. So this gives you an idea of what we can observe with our telescope. So on the left is an image of the Eagle Nebula taken with Pirate, and on the right is an image of the Elephant Trunk Nebula taken with Coast. Now, I'm not very experienced with processing astrophotography, so I imagine someone with more experience might be able to get even more detail out of these images. But I think as they are an absolutely spectacular representation of the depth and quality of the data we can get from these two telescopes. And now you've heard something a bit about the size of the two telescopes, I want to ask another question of the audience to see where your telescope knowledge is at. So hopefully everyone's still ready and poised with their fingers. And what I'm going to ask is, what is the largest optical reflecting telescope by effective aperture size, by effective mirror size? I maybe should have given people more time than 20 seconds, but tough luck. Okay, so yes, so a large proportion of you have fallen for my trick of putting the Very Large Telescope in there. In fact, the Very Large Telescope is not the largest optical reflecting telescope. It's actually the Large Binocular Telescope. So this consists of two telescopes right next to each other that feed into one optical system to make a just over, I think, 11-meter effective aperture. The Grand Telescopio Canarias is the next largest at 10.4 meters, I believe. And the Very Large Telescope is actually comprised of 4 individual 8.2 meter telescopes. They can be combined, but it's not done often. So that's why that's not listed as the top one. And the New Technology Telescope is 3.5 meters. Okay, so from some pretty images to some not so pretty images, let's look at some real science images. So my development and characterization of the telescope began with the deployment of software that allows us to track asteroids as they move relative to the stars in the background. So you can see how this looks in the GIF on the slides. The moving dot is the asteroid and the slug-like trail is the stars. Now, this isn't how you normally expect to see images of the night sky. And this is because we have to make the telescope move at the same rate of motion as the asteroid. And that's because the asteroids are really faint. So as they move, they would spread their light over many pixels and would get a really poor signal. So what we have to do is we have to track at the rate of the asteroid to maximize that signal in as few pixels as possible on the camera. And it's fine to let the stars trail because in general, they're brighter, so we can afford to lose a bit of signal. Now, moving objects and trailed stars provide a lot of complications when it comes to developing automatic tools to manipulate the data from these images. For example, if we track a really fast object for more than a few minutes, you get these extremely long star trails, much longer than you see in this example. Now, if you think about when you look up at the night sky, you see the stars twinkling, right? And this is because of things like atmospheric turbulence, which ever so slightly changes the brightness of the asteroid because of different densities of air between you and the star. Now you can imagine this happening while you're trailing your star across multiple pixels in your image. And this can cause the trails to become sort of like a set of unconnected blobs instead of a single long trail. So kind of, you can imagine like a beaded necklace versus a snake, for example. And this can actually trick the software that we use to analyze these images into thinking a single star is multiple stars, and we can lose all sorts of information from that happening. So this has actually been a major part of my research, to develop tools that can extract useful data from these images without the need for manual intervention and inspection for these sorts of effects. Now, next slide, I kind of want to give you a bit of an insight into the output that my research has produced. So I'm going to give you the highlights of a paper that I put out last July. Now, I'm not going to go into detail because it's just too much for a talk like this. I could give an entire talk just on the paper. So essentially, the purpose of this was, and this covers pretty much the first half of my research, was to characterize how well our telescopes perform within the field of asteroid science, and to make recommendations for how other similarly sized observatories can get the most out of their data as well. So the first thing we needed to do was to understand the behavior of various images that we take. So we have to take these things called calibration images when observing with telescopes. So there's these systematic errors when taking data with a telescope, and you have to use these calibrations to correct your science data. Now, what we aimed to do was to develop methods for determining the best way to combine these calibrations to get the best quality scientific data out. We also did a bit of mechanical characterization of the observatory. So you can think of we have a camera on the back of the telescope, and this has a shutter which opens and closes when we want to expose the pixels to the night sky. Now, as this shutter opens, the central pixels here in the image, they are the first to be exposed to the night sky, and they're also the last to be covered up when the shutter closes. Now, the ones up here in the top left are the last to be uncovered and the first to be covered back up. So when you take short exposures of your camera, there is actually a difference in how long certain pixels have been exposed to the night sky for. And you need to be able to correct for this and understand where it's happening in your data, because otherwise your scientific results could be modified by this shutter effect. As I mentioned before, we did a bit of development of data processing scripts and things like that to get the most useful data from the images of asteroids, along with all those difficult things that tracking asteroids throws at us. And we also did an analysis of the data quality that came off of PIRA and how we would expect that to translate across different systems and compare to other telescopes. Now, like I said, I'm not going to go through any more on this. It's quite detailed, so if you do want to read more, the paper is available free open access from the publications of the Astronomical Society of the Pacific. If you do want to read it and you can't find it, just let me know and I'll be happy to point you in the right direction. So the next thing I want to talk about is what we actually measure in the images that we get from these telescopes. So we want to measure the brightness variations of the asteroid, mainly. And there are three main things that cause brightness variations of asteroids. So as an asteroid changes distance from the Earth and the Sun, so say if it's closer to Earth, it would be brighter, for example. Now, we don't care about these brightness variations because we know why they're happening. It's because of the changing distances. So what we do is we correct these to some reference position so we can get consistent brightness measurements for any asteroid at any point in its orbit. And that leaves what we call the rotational and phase angle variations. So the rotational ones come as the asteroids rotate, because everything in the solar system rotates. And the phase angle is this little angle between these lines here, the lines that point from the asteroid to the sun and the asteroid to the Earth. And the phase angle you can kind of think in terms of the phases of the moon. So as you're looking at, say, a half moon, the phase angle is at 90 degrees. When you're looking at a full moon, the phase angle is 0 degrees, to help you visualize it. Okay, so if we look at the rotation of the asteroid, the rotational variations, on the left is a simulation of an asymmetric asteroid rotating with time. So the shape is actually a squished down version of the shape model for Itokawa that I showed on one of my first slides. And I've squished it down just to exaggerate some of the effects. So from this point onwards, I'll refer to this model as Squishikawa instead. So as Squishikawa rotates, it reflects a different total amount of light back towards the observer. Now, bear in mind, you can't see this shape rotating from the ground. It's just too far away. So we only see it as this tiny point of light on our camera. So we measure how that point of light changes, and we plot that like this. We plot how that brightness is changing as the asteroid rotates. We see we've got higher brightness as more of it is illuminated and visible from the observer. And this means that these rotational brightness variations, what we call light curves, give us information about the shape of an object and how fast it's rotating. And if we observe these light curves over loads of different orientations, we can actually build up a picture of what that asteroid looks like. Now, you'll notice in this graph that the lower numbers correspond to higher brightness. And that's because of the magnitude system that us astronomers use. It's the wrong way around. So brighter things have lower numbers. And we have the ancient Greeks to thank for that hiccup in our daily lives. And now, even though there are lots of asteroids, there are actually still very few which have well-defined rotations or shapes or anything like that. And it's really crucial to understanding these objects better. So as an example of what we're able to do with light curves, here is actually a shape model of the asteroid 159402 1999 AP10 that we have made from light curves measured with Pirate, and also some archival data available on the web. And I actually have a 3D printed version of this asteroid, but unfortunately I've not been able to get to the office to get it because of my self-isolation. But hopefully this animation shows you generally how it looks and how it rotates. You can see this isn't as detailed as Itokawa, and this is because from the light curves you can't find out information about craters or boulders or surface concavities and things like that. So it's an approximation at best. But nonetheless, I think it's really cool that we've managed to figure out roughly what an asteroid looks like from the data we've taken with the OpenScience observatories. Now, if we measure the brightness of an asteroid over a long time base, like I said before, this phase angle changes, and therefore so does the brightness of the asteroid. So if we think of the moon again, as it moves from a new moon to a half moon to a full moon, its phase angle changes from 180 to 90 to 0 degrees. So you can see how this happens here. So the phase angle here is changing. You can see how the asteroid changes, how it's illuminated. And this corresponds to these changes in brightness as this phase angle changes. And this is what we call a phase curve of an asteroid. Now, the brightness of the asteroid at this point, when it's illuminated completely front on, is directly related to the size of the object and how reflective it is, kind of like how we discussed before. And the slope of the phase curve, so how steep it is and things like that, is actually controlled by the properties of the material on the surface of the asteroid. So dark, carbon-rich asteroids have steep but quite straight slopes. But moderate brightness, silicate-rich asteroids have relatively shallow slopes but steep rises close to this zero phase angle region. And with Pirate, we've been able to observe around 15 phase curves of asteroids, allowing us to gain an estimate of the behavior of their surface material. And we've got a few more to go still before my observing campaign comes to an end in September this year. But this leads into my current work, which I'm going to try and just quickly summarize again so you get a flavor of the sort of research that goes on with these asteroids. So this is a slightly more theoretical study, and in this we're looking at actually at how these phase curves aren't only dependent on the material on the surface. There's actually effects related to the shape of the object. So if you take an object and say you're looking at the southern hemisphere, and as you change your phase angle, you instead then start looking at the northern hemisphere. If these two hemispheres of the shape look different, have a different area that projects back towards the observer, then this will actually cause variations in the brightness of the asteroid on the phase curves that are completely unrelated to the properties of the material on the surface. And these effects can cause the phase curves to do all sorts of weird and wacky things. So if you look at this on the right, the red data is a simulation where the phase curve is performing exactly as you'd expect it to. The brightness decreases as the phase angle increases. But under certain geometries, bear in mind we simulated both of these data sets with the same surface material. Under certain geometries and shapes, you can make the phase curves do completely unrealistic things like start to increase in brightness as the phase angle goes up. And this goes completely against everything we know about how phase curves should operate. And if you were to try and interpret the blue data and think of it solely in terms of the properties of the surface material, you would completely misunderstand what the surface is made of. So what we're looking at is how much this has led to misinterpretations of the properties of asteroids, particularly near-Earth asteroids, and how much this affects further studies, because other studies, like in the infrared, actually use properties from these phase curves as a first step in their analysis. So we need to understand how much that has impacted our previous work and how much it will impact our future work. Now, I won't go into any more detail on this as it doesn't really lend itself to this sort of talk, and like I said, I could give a whole talk on this, but I do promise that once this paper is done, that unlike some in government, the full unredacted Sue Gray report, the paper will be available online if accepted by the journal once we submit it. So hopefully that will be available within the next few months. Now, all of that detail towards the end was quite heavy, so I want to finish with some information on how anyone can get involved with the observatories. We run a free online course on OpenLearn, where in addition to learning more about astronomy, you get access to telescope.org, where you can request observations of stars with the telescopes, particularly with COAST. Once you get your observations back, you can then submit these to a long-term project that's monitoring certain stars. So you can get involved with scientific analysis with the observatories completely free and from the comfort of your own sofa or bed, whichever you choose. And then naturally access to the observatories is also available on various undergraduate and postgraduate modules of the OU, like SXPS2A, S382, S818, SXS810, S810. I think that's all of them, but I've probably forgotten one. So yeah, that brings me to the end of the content of my slides, and I just want to finish on one last question to the audience to make sure you're all still awake. So the question is, which of these is not a real asteroid name? You've got 20 seconds to try and answer again. Okay. So everyone, well, 2/3 of you have gone for 30476 Lewis Hamilton, and you would actually be correct. I thought I'd get more of you on this one. I thought some of you would think the 007 was a bit too on the nose in the James Bond one. So well done everyone for getting that. And the fun fact about the Mr. Spock one actually is, as much as it might sound like that was named after the fictional character, it was actually named after a guy's cat who was called Mr. Spock. And the International Astronomical Union subsequently banned people from naming asteroids after their pets after that happened. So that comes to the end of my slides and my talk. So thank you once again for having me, and I look forward to any questions that you will have for me. I'll stop sharing my screen.
Thank you, Sam.